help you revise because I will be working on this from now. So what did we do last day? So let's do some revision. So input was an X, and X is the input of the data. And there is layer 1, and it goes to layer 2, it goes to layer 3, dot, 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 layer n, and then finally the loss function L. So some of these layers have some parameters. Okay, let's say W comma B, or yeah, some of these layers have parameters, some of these layers do not have parameters. Like for example, this may be ReLU, rectified linear unit. So what we want to do is that we want to create a system that helps us calculate the gradients. Why? Because we want to update the gradients in the gradient descent. So let's try to understand from an algorithmic point of view, because what we have done till now is fully mathematical. Okay, so let's understand from an algorithmic point of view. So what is step 1? So brief intro. Now let's go to algorithmic point of view. So what is step 1? Step 1 is we always, so step 1 is build the system of layers. What is defined as a single layer? What, or rather I would call it a substep, but is it? Yeah, great, it's working. So substep, step 1.1, we should answer that what is this, what is the definition of a layer? What is a layer? Okay, we should understand this. And this is very important. We should understand it later on. We will redefine it. The next point is step 2. After building the system, what should we be able to do via it? What should happen via it? First is this somehow should contain the step 1.1. This somehow should contain. We will iterate it over and over again to get to a final converge to a final structure. So this should contain the parameters. Okay, like the linear layers, like W and B in linear layers. We have not decided how it will happen, but we'll understand it soon. Step 2 is what should happen through these layers. So each layer, so again going back, each layer, step 1.3, each layer is what? Each layer, so this also converges, like helps us understand what should be the definition of a layer. Each layer should have an input and output, right? It's like a function. But is it more than that? So more than that or less than that? So we also have to answer that. So let's say this is a sequence of functions, and also you have to have this sequence definition. Like, what are the sequences? What do you mean? What are the sequences of layers? Sorry, what is this sequence of the layers? Also, another question: what kind of layers are there? How many layers are there? Like how many different types of, how many distinct unique layers are there? These are the questions we need to answer. Like linear is a one layer, ReLU is another layer, right? All these things are layers. Softmax is another layer, sigmoid is another layer, etc. How many different type of layers are there? So rather I should call step 1 define a layer. Step 2 is build this system of layers. Build this system of layers. This is important. Okay. Build this system of layers. So probably I will this do like this, that you see it's an iterative process. Step 2.1 is build this system. What is the sequence of layers? Okay, so we first define layers, different distinct type of layers and distinct types. So this is step 1. The step 2 is connecting all these layers together in a framework. Okay, and this connection will be different models. So do you see, once you define this, understand this, that note this sequence or connection will lead to different models. This is important. So what if the next question is that can we consider the layer a single layer as a model itself? We can do that, right? So what if we consider a single layer as a model itself? Can we do that? That's important to know and understand. Can we just introduce any layer as a single model? Okay, can we do that? And if it happens, then what should happen? That's very, very important. These are all very important concepts that one should answer. Okay. Okay, what's next? So can we consider this as a model itself? Yes. So the next question therefore comes is, what should a model have? What should a model have? So that's a second question that comes up. So to answer this, let's answer this. So probably we will call it, yes. So let's do step 3. Probably you cannot see this, but yeah, I think you can see this. Step 3.1 is, what does a model do? Model takes an input X, outputs Y hat. Step 3.2, model takes computes loss between Y hat and Y. Step 3.3 is, I hope all of you can see this, right? Vivan, Anushka, Jadan, okay. So computes loss. But after computing loss, the model should, oh, there is one step missing. So there is a 3.4. So the model should do something that we are missing here. Model actually, if it's a sequence of layers, model, understand there is a modularity here. We want each layer to be a model, and we want a sequence of layers to be a model. So model should propagate the outputs, input, output, the IO pairs, the input, output through the layers. This is very important. So each layer has an input and output, and a model should also propagate the input output through a layer. So if you combine the model, that should act as a very big model, very big layer. Okay, so the entire model, so if you combine multiple layers, it will act as a bigger layer. That's the main idea. Okay, so note, combining layers is, so essentially multiple layers should work as a single layer. This is how it should be. Okay, so model computes loss, and model now backpropagates the loss from the loss L to the weights. Understand this. So the weights are updated. No. So now once the weights are updated, what should happen? Once the weights are updated, then propagates the not the law, propagates the gradient of loss. That is dl dy, gradient dl loss to weights dy. Okay, the gradients. Now we'll see what it means. We have already discussed this last time. And now once gradients are available, then we can do wn, we can update weights. That is w is equal to w minus whatever that learning rate times grad w or dw, or grad w, or we should call it dl by dy. Okay, because that's how, so let's call it dl by dy. So this is essentially what an entire model should do, and in fact every layer should do. And that's what, so the whole idea is that we want to build a modular structure so that each layer has a so we will now define the stuff. So each layer, so defining layers. So this is very important. This is what you do, thought experiments before you code anything. This is very important, guys. Defining layers. So layer should have, so layer should be, so what is the definition of a layer? It's very important. So okay, one thing we are missing here is that the layer should have some access to the weights, because inside the model, because the model is a layer and a layer is a model. Understand this. That's what we have discussed here. We want to build it modularly. So if a model is a layer and a layer is a model, the model should have access to the weights, right? So we have missed it here. So this tells you, note, model or layer should have access to the weights, should be able to perturb the weights and update this. So how about we define the layer as the weights? So it's like the property of the layers is the weights. So we define layer as an object, as a Python object, but it's like the layer is nothing but the weights. With values as weights. If you remind yourself again like this, so there should be an input to a layer, let's call it, yeah, and they should output to a layer. This is how you should define a layer, and the layer is defined as its object. And what should a layer be able to do? The layer should be able to get y if from x, but also get dl, dw, and dl, the gradients db, from the previous gradients. And this is tricky. So what we were wanting here, what we are trying to look for here, this is very important to understand. So let's try to define, and for that we will take help of this. So this is what we need in a layer. Okay, so what we need in a layer should be defined as, understand this very carefully. So let's try to so let's try to understand this with this example, that why do we need to define like this. So if you take this example of this, what are we doing here? So observe that we need to find dl. Let's call this let's make it simple. So we need to find dl dw. So how do we find it? We find it by this following way. First compute dl the output of these layers. So you see, therefore we need to, so if we define this output of each of these layers, we can define like this. Let's say x. So let's define y naught as the input of the first, y naught as the input of the first layer and output as y1. And then y1 is the input to the layer 2 and get output as y2. And y2 is going and being calculated as L. So to calculate dl dy2, so to calculate dl dw here, what we need to do? We first calculate dl dy2, then we calculate dy2, dy1, and you multiply this with to get dl dy1, right? And then we calculate dy1 dw, and then we multiply it with this to get dl dw, right? All of you understood this? This is the process. We first multiply this two, then we multiply dly dy this two to get this, and then multiply together to get this final thing. And then again we calculate dl y1 dl w here. Did you understand? Can you give a thumbs up or not? Like, if you have a question, please ask me. V1. So you see, there's a iterative for loop here. Kind of, it's happening over and over again. What is happening over and over again? Each layer, when you are backpropagating, it's happening like this. Each layer, if it's outputting dy and inputting x, essentially when you're backpropagating, you are calculating the loss dl dy, and you're also calculating, you're outputting, when you're doing backward, you're outputting dl dx. So when this is a forward, so let's define it here again. So this is the forward, layer forward. This is what's happening, the layer forward. And this is the layer backward. This is what's happening here. Okay, this is exactly what's happening here. So if you see the repetition, you see that layer takes input dl dy, observe this, dy2, and layer gives output dl dy1. So how this happens, that is happening inside the layer. This computation from to this is happening inside the layer. So there is some function inside there, and that function we call backward. Just like this function we call forward. Okay. So it's defining forward, and this is defining backward. So you see that here, to calculate dlw, we first input this, then this internally this is calculated, and this is multiplied with this to get this output. So this is layer internal, layer dot backward. So yeah, so this is happening inside, and then you get this inside, and this is happening again inside to get the dl dw. Okay, so the dl dw and dl, yeah, or dl dw when weights are there, weights are present. So both of these things are happening. The weights are also updated, and the previous input are also updated. So you can think like this. So you can also think like this, that mm, yeah, so you can think of a bigger one, and in this you can say that the DL DW is also calculated and updated. Okay, anyways, so the DL DW and DL DB is also calculated, but that's happening inside. So this is happening inside of the layer. In fact, something else is also happening inside the layer, but this is not given out to the. So understand, this is for the weights, not the layer. So there are two outputs. One is the weight based and is the input output based. In this case, also something is happening, but that is being outputted. What is being outputted? This one. Actually, this is being outputted, but this is not being. Yeah, the weights are not being outputted somewhere out there. It's inside the layer. So here, y is equal to the function of x. This is being outputted, but here this is not being outputted. Understand, this is very it is very careful understanding of what's happening inside. So this is how it looks like. All of you understood this, guys? Anushka, Arav, you joined late. I am not sure. I didn't also see you yesterday, so I don't know if you're understanding, but
I watched the video. Yeah, we had to go. I at least I went to this math competition, so I couldn't come yesterday. But I watched the video. I understand back
oh, super,
propagation.
super. So the whole idea is that we are trying to code this out now, and we are trying to build the concept so that we can code it out easily in a more fundamental manner. So we have now defined finally that what a layer should do. So layer should have a forward, layer should store this, and layer should have a forward and a backward. Okay, this is how we are defining. Okay, so now let's go ahead and start some coding. Okay, so let's build a layer, a single layer. A single layer, the simplest possible layer is a linear layer. So how do we do it? So we do class, and we have a linear class. Okay, so first of all, we use Numpy. So import Numpy as np. So class linear, and then what do we do? So we whenever, so this is a linear layer. So what is happening in a linear layer? Understand, the linear layer, when you are defining a layer, what parameter should you give? You should give, because understand, the weights are initially initialized. Okay, we don't need to give the weights. The weights are the property of the layer, but we do not need to give the parameters of the layer. So what we need to give is that what is the layer dimension, right? That is something unknown. What is the layer dimension? So if we do class, so now we will, so this is define a class, we will initialize it. Okay, and sorry, and then we are now going to define the input, and so dimension input, and or let's call it in and out dimension. Okay, and that's it. Now we are ready to define a layer. So now, as I said, a layer is defined. So these two parameters need to be defined by us. Next. Next is how is a layer defined? By weights, by the parameters. Here in a linear layer, the parameters are W and B, right? So we should define that. And when we define that, so the self actually helps you understand that, okay, it's inside. So it's corresponding to this. You can actually call this self.w in, as you will see, this is object, this is an object, class object. And this is when you define something, when you're defining something complicated like a layer should should be defined as, sorry, the values of the layer that should have the weights, right, the parameters, but it should also be able to have a forward function, have a backward function for the gradients, and many other things. So we'll see that. Okay, so what else? So self.w is something. So what is the dimension? If you remember, the layer dimension is what? The weight is nothing but a matrix of dimension, input and output. So what should be the output? So it's simple. It's input comma output dimension, and you have to build a matrix, a random matrix, because the weight should initialize randomly. Okay, so how is the weight initialized randomly? So let's understand. Okay, I think I need an indentation here. Is np.rand random dot rand. I hope I have written correctly. Yes. And okay, it's rand. And the input dimension and output dimension, right? So if I just, I'll do it here. So this 1 comma 3, you will see print w comma shape, w dot shape, it's 1 comma 3. So we have this 1 comma 3 dimension out here, or let's, sorry, input comma output dimension. Okay, so now we also have to define the bias. So self.b is np.random dot rand, and it just so what is the bias? The bias is just for each output dimension is there a different bias. So we can just add it like this. Yeah. Can also define like this, but yeah, that will extra add a parameter. We have to unsqueeze it then. Okay, so this is the definition of the. So if you remember, this is the definition of, we have defined the layer w comma b, right? But we have to also have some functionalities of this layer, the forward and the backward. So let's define a function forward. And what should that forward function include? For a linear layer, the forward function should include just x. Any layer, it's a single x. And what should be the output? The output of this, let's call it y. Y is what? So x, understand what should be x dimensions. You have to be very careful about this. So let's define x, and y should be, so x dimension, x is of dimension, should be some a comma input dimension. Otherwise we will not be able to use it, right? So y is equal to x multiplied by self w plus self p. Sorry, it will be output dimension. Input dimension. Yes, x is input dimension. Then w was input comma output, and then bias is output. So that is added to the output. So this. So we can check it out. X is equal to, let's say, NP, same thing. It should be okay. Input dimension, let's call it 2 here. So let's call it 1 comma 2, um, or 10 comma 2, and bias is 3 comma this. So we have to print X times Y plus BW plus B dot ship. It's, you can see 10 input, 2 multiplies 3, and it's 10 comma 3. There's an issue here. The issue is that, let's just give me a minute. Yeah, yeah, it's absolutely fine. Because if you remember, so this is something called broadcasting. So what is happening is that for the output dimension, understand this, for the output dimension, okay, let's understand this carefully. The output dimension is 3 here, right? So this X times, just give me a minute. Yeah, yeah. So this, yeah, yeah, yeah. So yes. So what is happening is that, yeah, actually it's this. So the input dimension of X is nothing but how many input X are there. So, but yeah, if you do 10, that means there are multiple inputs together, bunch. So we will learn that it's called a batch. So essentially it's like this. So input is a 2-dimensional input, or let's say 5-dimensional input, then 5, and it goes to a 3-dimensional output. And what each of those 3 we have the bias. So that's why it's coming like this. Okay. All clear, guys?
Yes.
So here self this, and I think it's pretty good. So return Y. This will be of dimension A comma out of D. Okay, Vivan, Anushka, all good? Or Arav, or Jaren?
Yeah, I understand.
Okay. So what's next? This is forward is good, now the backward. So we have to now get the gradient. So sorry, backward. So now we have to understand, what does the backward need? The backward, here the input is X, but the backward needs DL dy. So what we call it here is, we have a specific name for it. We'll give it a specific name. So we will call it grad underscore in, or out. Out. And here we call it grad underscore in. Okay, that's the specific nomenclature we give. So your thing is coming from out, so it's grad underscore out is coming. Okay, now what happens to this grad underscore out? That's where you need to just remember a few results of how everything happened. If you remember it, I do not know if you remember it, but let's do some revision if we can. Just give me a minute to see. So y is equal to, so if you remember that, we can actually write here. So let's write here. So if you remember, y is equal to, what's happening? X w plus b, x times w plus b. So this implies that sorry, this implies that the y is the output. So let's say we already have, because the input is dl dy, okay, understand this, and we want to get dl dx. So we need to just sorry, dl dw. So we need to multiply what? We have to find actually dy dw, and then we multiply it, right? So find this and multiply with dl, the input, dy. So here this dl dy is grad out dl. So there will be two things. One is there will also be dl dx, as if you remember. So there is an issue. Yeah. So this is something we call. Let's see. Just give me a minute. Just give me a minute. No, absolutely fine. So we actually call this grad. This, yes. So this dl dw is grad, dl dx, y is grad out, dl dx is grad in. And we will save. We need to save because we need to also update. Understand? We need to update the. So we need to save this. So to save this, so somehow, so we need to remember, we need to save, just like we save the weights, we need to also save the gradients of the weights. That is dl dy. So let's do this step by step. Need to save dl dw and dl db, and everything here remains the same. Okay, we need to save this. You see, save this. It's very important. So let's call dl. So we have got grad out. We need to find this. So let's call dy dw as. So dy dw is what? Y is equal to this. So this implies dy dw is. Can someone tell me what is dy dw? X transpose. Right? It's simple. So X transpose. So understand, we are getting this X, we are saving this X here, we are getting the X here. So we need to save it somewhere so that we can save it, use it in backward. So dy dw is nothing but transpose of this X transpose. Okay. And so dy, so now the next step is to find out dl dx, sorry, dl dw. It will be nothing but grad out, that is dl dy. So let's write it in a better way so that we understand, remember more than that. So this is nothing but grad out. Okay, so we need dl dw at the rate dy d, right, to get dl dw, right, just like gradient descent. I'm just writing this all down for you, and also iterate dl dx, right, the input is x. So dl dx will be nothing but dl dy at the rate dy dx, which is not done yet, So we also need to find dy dx. So dy dx is nothing but I think it's just y transpose, same thing. So self dot y dot transpose. Got it, guys? We have to just check whether just probably here we have to check one important thing is about the dimension. So just let's remind ourselves that x was a, so this will be this. So this is very important, okay? A. So I have a hunch this will be let's do it w wise out d and in d, and we need to multiply dy dx with this. So dl dy will be the y output is, see, y dimension is this out d. Yeah, I think it's perfect. So this one, understand, it's something, let's say b comma out d. So you b comma out d and out d comma this turns out to this. So it's like dl dw, this b comma out d, and dy this. You have to check this one. D d dy dw is, what is x dimension? Hmm. Yeah, so here is the issue. So you can see this is not correct. This dldw and dai So this is correct. Okay. You can see that dldw is this at the rate. This is important. Okay. But this is not correct. But you know this will be something like this. So you have to change it, the order. So dldw is this dydw, and dl this. Let me just check. Just give me a minute. So grad out. So hmm, X transposes. Hmm. grad out is dl dx should be, probably I'm missing something very simple. Um, the int dimension. Oh, I'm thinking about dl dy. So dl dy should have the same dimension as ind comma. Yeah, that's true. dl dy. So ideally, it should be before, because this is input is this at the rate dl dy. But this turns out to be, because dy should be, but this turns out to the fact that the input and the output dimension. Ah, I see. Yeah, yes. So you see this, yeah, I think this should be A actually. So yeah, so the thing is that this A, so this is what I was, if you remember, I confused you, probably also myself here. This A is nothing but the number of samples. Okay. Sample size. So you can, so this should remain same across the layers, right? That should remain same across the layers. So ideally for one data set is just one, but yeah, so that's why you can see that. So this is why you see the dimension analysis is very important. Do you guys understand this? So this is something you have to do very carefully. That in and out of. So n is, yes, the n is the number of samples coming in. All good? This is a one-time activity. Okay. Okay, so now we have got this. So what's next? The next part is to understand, actually to write down the output, the grad in, that is dl dx. So return. So let's define this as this and return grad in. Okay. I use so many variables to just make you understand. This is very important. Okay. So and that's it. That's a layer, guys. That's just a layer. Simple. So let's try out this layer. So let's run it. We already have the x input. So we multiply it to make it small. Okay. We multiply this to make it a bit small. And we can also make it np dot zeros. Yeah. So let's try out it. So x we need, so first we need to define this. So the linear, we need to define this in command. So this is a linear layer. So let's say L1 linear layer, which input is 3 and output is 5. The input and output dimensions of the weight. Remember, it's a weight, it contains the weight. So now it's simple. You will understand it's simple. So the L1 dot forward of x. Now we have to define x. So if you define, let's say this is the y, if you print y dot ship, so this will not happen because here the input is 3. So the input dimension has to match. Like, let's see what happens here. Let's see if you have 6. Yeah, you will see it's different. So it should be 3. And it turns out to be 1 point. Did you understand, guys? So x is the input. It should have 3 input features. And it has forward. Now let's do the backward. So the thing is, for backward, we need the grad dot out, which we don't have. So we will do it soon when we have the loss function. So we will have the loss function soon. So loss function is, let's say, uh, let's assume y hat to be again np dot rand, but here, so the input is 1. Okay, 1x. So there is so one data point. So this 1 is one data point. So n and n. So n is one data point with 3 input features, but y is just one data point. Okay, it's a regression problem, let's say. So if you also print y hat dot shape, something is wrong. Okay. Oh, it is happening. Yeah. So you can see that y hat. Yeah. So now y hat is not this. It's the output features. We have to have again another linear layer. So L2 is linear 5 comma 1. It goes to the 1. So now we can do y hat is so this is y. So this is the input data. Okay, understand this. So this is y hat. So y hat is not this. So y hat is L2 of forward of this, right? So L2 L1 of this is output layer of 1, and then you can see both of them are 1. So actually we have to remove the so y hat, I think you have to do y hat is unsqueeze. There's a, I forgot the code to remove the access. Just okay, let me. Oh, order access dimension from. I think there is in torch it's squeeze, but I'm not sure. Does it squeeze work here? Wait, squeeze at the one dimension. Yeah, great. Oh, squeeze works here. Super. So we squeeze it at dimension 1. That means this. So it becomes same. So it's a single number now. So now the loss turns out to be, but we have to find the loss gradient. So if you remember the loss gradient, so dl by dl y hat you have to find out. So dl by dl y hat is what the gradient is. So dl by dy hat is what the gradient is. So L is dy. Understand this. The loss is y hat minus y whole square. So if you do dl dy hat, it will be 2 times 2 into this times, that's it, 2 into this. Okay, Just a single number, understand this. So if this is 2 into this, we can have dl dy hat as the same thing. Yeah, I already have it defined. Both of them are defined. Okay. So now this is the grad input to the backward here. So there are two of them. So let's do a grad input here. So first gradient. So grad, understand. So here is the diagram. So you have to remember the diagram often so that you don't forget. So x, then L1, then L2, then y hat. So y hat is the output here actually. So understand this. This is one layer. Let's call it y1. And then this comes in. And let's call it y hat. And then it goes to L. Okay. So this y1 comes in here. And then same thing goes in here. So get the final loss. So this is the structure. So we have found dl dy hat here. Now that is on this axis, on this. So dl dy hat is now grad out. Now we have to calculate the grad in for this layer 2. So this is the current grad. So grad out is now this. Okay. So let's calculate the grad in. So the grad in now is here. Now this is the grad out here on this axis, on this arrow. Now we have to calculate the grad in. That is dy dl dy1. That is, how would we calculate it? We just get this, the grad in here. That is dot backward. So the grad in is L2 dot backward of, it takes the input of the grad of this grad out. Now grad out, the next grad out of the next layer becomes a grad in now. So this same grad in, understand this, the same grad in becomes a grad out of the next layer, right? So this grad in, grad out becomes a grad in on the next layer, and we can do the same thing again. Grad in is L1 now. Okay. Now understand this. While you're thinking, okay, how are the weights getting saved? You can see here that, okay, I think you have to define like this, because we need to access this later. Yeah, we need to access this later on, right? So we have to call it now. Call the weights out now, right? So without this, so we also have to do self dot dy dv is, I think now it's just yeah, it's just so the b is the, so understand this is dy db, so that's 1, but that 1 is, so we need to actually find out. Yeah, to be very honest, we do not need this. Yeah, we actually do not need this. No, we need this. Sorry, sorry. I am doing something wrong. Let me think. No, sorry, we do not need this. We need this. Self dot this. We also need to have this self dot tldb. So again, so yeah, dydv we have, and then just let me think once, okay? So because we again need to have this at the rate, it'll be the same n. So yeah, so b is a single dimension. Remember that. Yeah. Uh, no, not single dimension. Just the out dimension ones. So if you observe dv is, let's see what is dv dimension. Yeah, just out d, right? So we need um, here it should be one dl dy. Yeah, this dl dy. Yeah, so dl dy is in out. Yeah, so okay, perfect. Yeah, this is n this, so it's out dimension. Yeah, it will be. So you can directly write here. Yeah. So do this calculation once. As far as I remember, it will turn out to be the sum of. Yeah. So this will be np dot mean or sum. You have to do the calculation. So anyways, access is equal to 0. So we have to just check this out, okay? Check this calculation out once. Uh, but yeah, so this is what it will be. And here, again, the same thing will happen. But understand that we can access this now. So we can access this self just by calling the linear. Okay, so we can just access the L1 updates here or L2 updates, doesn't matter. We can call the, yeah, because now the weights are updated there. So when you call this, the weights, the gradients are already updated. Now we are calling the gradients for the next step. For example, self dot L1 dot W. Yeah, L1 dot W. Yes, this self dot W needs to be updated with this self dot DLDW. Is the previous one This is the previous one minus, let's say, the learning rate times this. Perfect. The learning rate is not defined. Let's say this is 0.001 minus this. Similarly for the B, and similarly this holds for layer 2. Okay. So dy dw, where did I put dy dw? Oh, oh, wait, what? Dy dw. So something is wrong here. So let's see. Did I not update the? But the x is already defined. There may be a pro. No, it shouldn't be the. Uh, uh is it because I have defined like this? So x is defined like this is x for L2. So what is the problem? Linear just no dy. Self dot. Hmm. You want to say something, anyone? Okay. We have to check what's happening over here.
Wait, so can you go down to the error? I think it's showing when you define self.dlw. That's the line that because it has dyw in.
Oh, sorry. Thanks. Okay, now there's an error of so it's an error mismatch where what? Print. Hmm. Print. Okay. This too. Ah, this probably because this. What if we define like this? Let's see. So it's saying that okay, so DLD, why is this? dy dw at the rate. I mean, trouble already. Is it because where is the dimension mismatch? Oh, I think I'm looking at this wrong one. This is absolutely fine. This is where it happens. Okay, this is okay. Find this. Okay, so dl dy and dy dw is this. So we need to find. I am doing something wrong. So we need to multiply this to get dl. Oh, interesting. Because is it? Yeah. You see, because the loss function has not the one defined, so you have to unsqueeze. So the loss function, so dl dy, the grad out. Okay, so that should be grad out is np dot np dot axis. Oh. Yeah, now it looks good. Perfect. All good, guys? So if you have now 10, you will see that DLDW is this. First layer, it's coming out to be this. Second layer, it's coming out to be this. And finally, all good. So this is the beauty. Okay. Vivan, Anushka, and Jaren. That's why you see dimension analysis is so important. I did a small dimension analysis here. And that's why you should always go out and check print. Okay. So this is pretty good. So you can see it's working. But it's just one step, right? It's just one step happening here. So you have to also make sure that this step happens for n steps. This thing happens for n steps. So how we have to also do that. So, but the model, the layer idea is pretty ready. The layer idea is pretty ready. So you have to understand how the n steps should happen together. So let's try to do the n steps now. All of you comfortable with this? The most important idea is done. Did you understand? Most important idea is done. You have to just now reiterate the for loop now. So instead of reiterating the for loop, what we'll do is that understand that this is, so understand this thing. So it's this weight update is also based on layers, right? So if we can define the layers and do the weight update, that will be great. There should be some way to collect all the layers together. So we will define now. So this is a model in itself. So we will define the model now. Okay. But this abstract idea should be remaining the same. Let's define the model now. Let's say model. So class model. Def underscore init underscore self comma. Now the model should contain what? This is important. If you see, what should the model, how did I define? I actually defined 3, 5, 5, and 1, right? This is what the model should contain. And we'll try to do it for just regression, just this same thing. So what we will do is that we will define the dimensions. let's say for example 3 1 3 2 3 1. Okay, so this is the input dimension x1 x2 x3, then it goes to let's say 4, and then it again comes to 2, and then, or let's say 3, and again comes to 2 and then 1. Okay, so it increases first and then keep on decreasing. So this is the layers. So essentially it's defining L1 L2. So what we'll do now is we can define self dot layers is equal to so we need to make a list of all these layers, right? So we can append the object. So let's see what we can do. So to append the objects, right? So we define a list. So for I in range of the length of dimensions, that means this should be the input output. We have to make sure that we properly give the dimensions. So we will go from 3, and for 3 we will add the layer 3 comma 4. We will go to 4 and then add the layer 4 comma 3, and we'll stop here. So it should be -1. Self dot layers, okay, dot append will append each of the linear layers.
Wait, so can you repeat what dim like the dims variable is? I didn't.
The dims is nothing but, you see, we are defining the linear layers, right? 3 4 5 1. So it's essentially 3 4 3 4 4 5 4 2 4 3, like this. So instead of defining like 3 L4, okay, so we are defining just the, because that's what defines the linear layer, the weights. So we are
Okay.
defining 3 4 4 3. Okay, essentially this means here L1 is equal to linear of 3 4, followed by linear of 4 3,
Okay.
followed by linear of 3 2. Okay, and here you have to just append the linear layers. Or understand, appending linear layers is nothing but making it a linear layer only. So ideally what we want is we will add another such layer called ReLU. Okay, it will be very simple, and we can alternately add ReLU and linear together. Just give me a minute. Yeah. So we can add linear of dimensions of I, comma dimensions of I plus 1, right? I comma I plus 1, I comma I plus 1. So I already the ReLU layer written. So let me just write the ReLU layer so that we can just do it. Or actually ReLU layer is very simple. So let's define the ReLU layer. Class ReLU. Okay. Def underscore init underscore score self. We just don't need anything else. Okay. There's no parameter in value, right? That's the best part. So in that actually we do not need this init because we are not initializing anything. Def forward self comma x, so some input is coming. Def backward self, there is yeah, self comma grad out. That's right, grad out, yes. So we have to return grad in and here. So it's nothing but what is value? It's max of 0 comma x. So y is equal to max of 0 comma x. So return y, right? That is max of 0 comma x. Um, or in other words, yes. Uh, or in other words, one way we can do it is we can find out where x is greater than 0. So let's call it mask. Is all the places where x is greater than 0. And what we'll do, this mask is binary 0, 1, 0, 1, 0, 1. So wherever is less than 0, it will be 0. Wherever is greater than 0, it will be 1. So we will multiply x times that mask. And if you do the derivative of it, you see it's nothing but x times something. So what will be the backward? So if there is a y comes in, that is the input to the ReLU. So del y, this essentially grad out. Okay, so let's write it again here. Del L, del y is the input, right? We need to calculate. Sorry, we need to calculate. Just give me a minute. We need to calculate del y, del x, and x, y is equal to x times mass. So del y, del x will be what? Just the mask, right? But again, we cannot take the mask here because mask is not defined. So we need to define self dot mask so that we can get this self. We can, yeah, that's important. So this times grad out, or probably grad out times that. Just check because just check the dimensions. So, and this is nothing but grad in is nothing but this. So return grad in. Did you understand ReLU, guys? You don't know? It's very simple. This is the most important structure to understand. And if you do it once, it's easy. All good? Vivan, Anushka, Jatin? Okay. So we have grad in here. So now what we can do here is that we can append this, and for the same I, we can append the ReLU, right? Because it's linear ReLU like this. Except the final layer. Okay, except the final layer. So we can add, for the final layer, we can add this. Or we can say that if I is or we can also do like this. For the last layer, we just append self.layers.append linear, and this is length of dimensions -1, comma this. minus 2, comma minus 1. Perfect. So this is the last 2 comma 1. So if it's before that, we keep on appending like first linear layer and then ReLU, linear layer, ReLU. So this and ReLU, this and ReLU. Okay. Well, for the last there is no ReLU because directly goes to the 1. Got it, guys? Okay, Anushka. Others have answered. Okay. I hope you understood. So then let's do the def forward. So def forward against self, because again our model is a layer. So def forward is nothing but q, forward for all the layers, right? So x, we have the x input as usual, but what we will do is that for layer in self.layers, so every layer is a layer, and every layer is actually an object. So we can call all those layers. So what we can do is that for the next layer, x becomes the output of the first layer. For the first layer, so its first 0 happens, and then it becomes the next x for the next output, right? And def.backward is same self, but here we need the grad of the loss. Okay. So grad out. So we will see how to do that. Yeah, because we need the grad out anyway, because we have to, yeah, we have to define this grad out. Yes. So we'll see what to do. So again, for here, the same thing happens, layer in self layers, but here we have done it again. The grad out becomes the grad in, right? So the grad out is nothing but the output of the layer dot backward or grad out. Did you get it, guys? Oh, by the way, I forgot something. So there's an issue here. So we have to reverse the entire thing. Understand this. So here we are doing in linearly, but we are doing backward from behind, right? So we have to reverse the entire layer. Okay. So this is nothing but a model as a layer only. But something needs to happen here. That is, the weights need to be updated in this model now. That is, weights of all the layers should be updated. So all the linear layers. So there are two kind of layers, linear and ReLU. So what we will do here is that we will update the weights. How do we update the weights? It's simple. So we'll define something called step. And what I'm doing this, I'm redividing these names because as I will do PyTorch next week, okay, you will see all this comes up naturally. All this backward step are already there inside. So you will understand that actually they are doing the same thing that we are doing right now, but we are doing from scratch, very fundamentals. So step, now in step, what should happen? In step, the input. So what is the step? Step is the weights should get updated. Y is equal to y minus learning rate. So the learning rate is unknown. So let's call it 0. Let's define it this. And the update should happen for all the layers, right? So we have for layer again. But understand, as we do this grad in, as we do this grad out, okay. Oh, just give me a minute. We have to return something here. Got next. Because we'll use this for the loss, just like we used it here. So this return is nothing. So this forward is nothing but this. Understand this. So this is forward. This is the def model def forward. Okay, this is, so it's output y hat, and then loss calculation and initial grad out definition here. Here's a data set. Here's a model definition. So we are defining the model now. So instead we are combining them. So grad out, yeah, this new thing is that now the model.backward is happening. You see? Yeah. And once the model.backward is happening, the final stuff is here. The model.step. Okay, so this is really helpful now, because you see in all of them, L1, L2, all the layers are involved. So we have done this model.backward, you have done model.forward. This we are yet to do. We will do it later on. And here we have the model.step. In the model.step, for every layer we are doing this. So it's simple. For layer, again, for layer in this. So understand, as I am doing this, so first you do backward, right? So as you do backward, the weights are updated. Understand that. Sorry, the gradients are updated. The gradients are saved now. That is DL, DWs, and DL, DB are saved. So I copied it from here. So instead of L1, we will just replace it by layers. That's all the layers. But understand this, we cannot do it for everyone, because ReLU also has a layer. So we have to check if layer, if is instance. Yeah, so you have to check object. So layer comma linear. If it's linear, so then only we can do it. So if it's linear, then only we can update it, right? And once it's updated, that's updated. The weights are automatically, because understand the weights are inside the layers, right? And that's what we want. And again, the model is entirely updated now, and then it will happen again. So, oops, where it is needed. Def. Oh, okay. So now what's next? The next is we will run the epoch. For multiple epochs, it will happen. So let's call it n epochs is 100. 100 epochs. So the model is, let's define the model first. So our model, let's say our model is model. And in this model, we have this dimension saved like this. You can actually change the dimensions. We can actually change 7 like this. Okay. So our model. And now what we'll do is that for epoch in range of n epochs, for all the epochs, for each epoch, what we will do? Step number 1, for each epoch, step number 1 is for each epoch, the step number 1 is to get the out. So let's check this example. To get the model.forward. So y hat, right? So let's define the data set here, the same thing. And stuff. So data set input is let's say 10, or let's say 10. Okay, 100 epochs are there. For step 1, model.forward. The y hat is model.forward. So y hat is our model dot forward of the x. We have already defined x, right? Step 2, loss. So once we do this, what happens is that, understand this backward. Understand this backward. Actually, for example, this backward uses this. In the forward, we define the self.x, right? So this backward also uses self.x. So once we do this forward, the whole structure is created. All the values, the forward values are created. Now the loss we will just do it similar to here. But ideally what happens is, for the loss, it has its own function like this. For advanced, for all the losses, it has its own function. Okay, it has its own function. So for example, yeah, so for all the loss, yes, it has its own function and own. So but yeah, so you get essentially the goal is you can make it into a function for any function, but you get the grad out. Okay, since we already done it for, we will not waste our time. And step 3 is backward. So once the loss is calculated, we will now find the gradients. It's written here. Y hat is equal to X. Okay, and here you can now do gradient. So now again, let's go back and see what we have done here. Yeah, the LR is already defined, but we can again define the LR. So model.backward. Just we need to do that because there is no output. Model.backward. But remember, in the backward, LR is 0. We can put it 0.02. Okay, so you can change it here. Now this is not complete yet because we have not updated the. So update parameters now. So our model dot step. Now once this, so oh, I'm so sorry, this step is in this. The backward has any parameter? Yes, the backward is grad out, which I have not given yet. So the backward has this grad out. This is the initial loss grad out, DL dy hat. This is the DL dy hat. This comes in and all the gradients are passed, the gradients are updated automatically. In where? In the self dot. Understand this. Where they're updated? In the self dot dlw and self dot dlb. Yeah, so there is no gradient in ReLU, so there is no such thing here. I'm just double checking. So now once we do this here, I think everything is all right. Yeah, I think that's pretty good. Finally, yeah. Actually, we didn't calculate the loss. Let me calculate the loss also here. Because loss will also be updated, right? So what we can do is we can see how the print loss is changed. Fingers crossed, I hope this works. So, wait. Okay, so here the ReLU is missing, they're saying, which makes sense. Yeah. Oh. I somehow missed the ReLU. But here. ReLU has this. So what's the issue? Of course, missing one required positional argument. forward, we have this. What if we, so does this happen without ReLU? Let's see. Oops. Issues. Hmm. So where is this happening? So this is what happens. Now, let's say you are working with a model library. Essentially, your goal is your goal of debugging is to go back and actually fix those, like do this debugging one by one. So what you do is that you have to go back and see where it's happening, in which layer it's happening. So is it happening? Uh, uh Wait. So is it happening like for like this also? Okay. So let's say we do it simple. No, it's still happening here, which shouldn't have happened for the simplest possible case. So input. So X is this. So in this case, we have to see this step forward. So let's do one thing. Let's print layers, I hope. Oh, self.layers. Oh, I know it's gonna be giving linear objects. So one way to do it is, can we print x.shape, input shape, and do x.shape. So first is 10,3, and that's where the issue is happening. So somewhere the layer definition is problematic, because this was not an issue when we did it before. So somewhere the layer definition here is problematic. So I comma, yeah, uh, yeah, I think yes, this is an issue, I believe, big issue. I did it wrong here. The dimensions that we want. Is it because of this? Yeah, so you see we had an issue of, I actually took the, what? Ah, now that this is done, it looks like its issues are gone, in the sense that, okay, say 3, 4, 1. I hope. Oh, nice. See? Oh, it's working. Wow, this is good. I'm happy. So the final layer is not somehow working. No, or is it? Yeah, it's not working. But yeah, I'm glad it's working now. So did you see, this is how you do debugging, okay, guys? That's why I wanted to code live in front of you, so that you understand that it's not linear. And this is what you have to learn. All good? Okay. Next, final stuff is, yeah, so it's saying that the bitwise XOR is not supported. Yeah, so let's see. So there's some loss issue. So let's see. Because understand, the forward is okay now, the backward is not fine as of now. So I am also concerned about the backward. So print So let's see where it's happening. It's happening at the loss only. Ah, because I remember. Yes, 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 yes. Ah, so so y hat. So print y hat shape y hat dot shape. So it's 10 comma 1 naturally. So okay. So what we can do is I see y yeah. So because y is defined as n comma 1 n and y hat is n comma 1, so we have to just squeeze it here. I think that works. Not here, probably here. No, still not happening. So y minus y hat works. So let's see. Y hat minus y, does it work? Oh, it works. So y hat minus y is not a problem. So probably the square is the problem. So we will do np dot square. Is it a problem now? Dot shape. Okay, 10 cross. Ah, yeah. So this is the issue. So because of that one that is being, so we have to squeeze it actually, to be honest. Yeah. So y hat should be squeezed. So y hat is equal to y hat dot squeeze in 1. So let's see. Looks like everything worked. I'm very happy now, though. Yeah, looks like everything worked. Nice. Superb. See, this is the power. We didn't print anything, or did we? Yeah, we printed the loss. So probably we printed a lot of things here. We have to remove that prints. No, we remove all these prints. What else prints are here? Loss. Yeah. Input ship. Oh, all these things are probably printed from here. Oh, I didn't update it. Why is this coming out? Print TLDY? Did I print that? Probably when I defined layer, I printed that. Yeah. Oh, I also didn't update it probably. Oh, perfect. So 100 losses are being, let's for ease, let's do 20. So you can see 20 losses are here. Super good. But you see the losses are of, so these are individual losses. Okay. These are individual element losses because everything is defined individually. So we have to just take the mean of that. So yeah. So these are individual losses. So this is as of now, yes. So each step should be the loss is minimized, and in fact, yes. So in fact, this should be divided by, this should be made sum. So that should be np dot mean, and this should be np dot again mean of this. I mean, if you remember, I said that if loss is summation of 1 by n li, so it's, yeah, the same thing. what is happening here. But again, there'll be an issue. Let's see. I have to now search because time is going on. Ah, yeah. So yes, because instead of doing this, they're suggesting this. Yeah, see, it works now. Super. Yeah, so instead of np.mean, we are just divided by n, because when we do np.mean, it collapses to a single 0 dimension. So if you see, if we don't do this, and if we do what we did before, np.mean this, and if you print the shape of it, it will be nothing. You see, it will be nothing, like it's a 0 dimension. Okay, so that's why it was finding it hard to add 1 dimension. Probably it can be done if we do this, or so better is to define like this, so that this y hat minus y dimension is remained. Got it, guys? Did you understand? So this looks pretty clean and awesome. Superb. And I hope you learned something from here. Hope it was useful, and this is extremely good. I feel so happy now. So great, superb. So next day, we will learn. I will send this code to you guys. We will learn how the same thing happens in PyTorch, where we do not do it from scratch, but you will see all this dot step, dot backward, dot forward. Dot forward is not specifically there, but it's underlying. All these things are done underneath using are using libraries, and we can build a large number of functions. And also, we will find out how to train a model. That is important, like the structure of training a model from scratch. That is very, very important. Structure of training a model from scratch, like train, test, data set, validation, train, test, validation, cross validation, bias, variance, trade-off, how to evaluate a model, performance, for classification, for for classification, for regression, how do you evaluate a performance, how do you define the loss functions. We have already defined the loss function, evaluation, and all these things. And for example, we have a concept called batch size, so we have to talk something about stochastic gradient descent method. So next day it will be about mostly this, and the final next Sunday will be about using PyTorch, and you will see the same things that happens here. Okay, and then the project will be given to you, and you have to do the project. So that's all, guys. I hope you enjoyed, and thank you for your time. Bye-bye.
No, bye. Thank you.
Bye.